Vai, vai. Bonjour, bonjour à toutes et à tous. Donc, deuxième journée de conférence, première conférence de la journée. Olga Beatrice Carcassi, une partie de vous la connaît déjà parce que vous êtes en atelier avec elle, qui est chercheuse associée, on peut dire, à Columbia University et qui nous présente cette conférence Designing Regenerative Cultures Between Ecosystemic Design and Digitalization. Merci Olga.
Merci à vous. Vous m'entendez? Okay. I'm going to do the presentation in English, but please, if you want, you can ask me questions in French. That's okay. It's just because it's easier for me, the technical terminology. Okay? So first of all, thank you for the kind invitation. I'm very happy to be here. And today I'm going to present you my past works and also some sort of path that I did from my PhD up to my current position inside Columbia University in the Natural Materials Lab. So my husband always tells me that I'm a mood killer at every party, so I'm going to be very quick and tell you the why that guide my what and the how during my research path. I think we all agree that climate has changed, and even if there's a lot of people who still don't believe in that. And I don't want to bother you because I hope that I'm well aware that all of you may know the physics, the science behind that. But I really want you to keep two important concepts behind that, which are additional greenhouse gas effect and concentration of CO2. So every time that we see, that we are told that the climate has changed and there's a rise in terms of temperature, we have to consider that the cause, it's an additional greenhouse gas effect, because in the planet, in the atmosphere, there is a natural greenhouse gas effect, which helps us, as you can see here in this meter, to keep the Earth around 15 degrees Celsius as an average. And without this greenhouse gas effect, the average temperature in the planet would be minus 18. So this is a natural effect that it's been happening, and it's part of our atmosphere. But the problem is that human activities are adding an additional greenhouse gas effect on the planet, which is, maybe you heard about the increase of 1.2% degrees of the temperature of the atmosphere, 2 different scenarios, and those increase in terms of temperatures are related to this 15 degrees Celsius, which is the temperature of the average temperature of the atmosphere before the Industrial Revolution, okay? And of course, this increase, this additional greenhouse gas effect, scientists were able to correlate to the increase of human greenhouse gases that were released in the atmosphere. And you can see here really the concentration of these greenhouse gases where the CO2 is considered one of the most abundant in terms of emissions from human activities in the atmosphere. So just to have a common ground in terms of these concepts. Well, so who's responsible for these emissions? We are inside of architectural and built environment context. So you heard that in the past 20, 30 years, there was a huge attention on the thermal and the operational emissions of buildings. So you heard a lot about we have to have more energy efficient buildings, so on and so forth. But nonetheless, if you look at this graph, I'm not going to go into the details, but I really want to show you that this research that was being done in 2013 really want to grasp the difficulties in mapping and finding all the correlations between services, sectors, and final emissions. And even if thermal comfort has been really the focus of the past 30 years in terms of research and endeavors, if you look at also what are the construction, buildings, and infrastructure, so all the emissions that are coming from materials, production of materials, so on and so forth, they're really dispersed in different path, so they're very hard to grasp. So what happened is that in the past, we became, with the advent of the new building codes that required for the building to be more energy efficient, we became very, very good. We made incredible progress for what is heating or cooling the buildings, but we didn't do a significant progress when it comes to materials, so how we build them. So in this graph, I don't know if you're familiar with these two definitions. The embodied carbon, it's all the emissions that are related to the material production, transformation, material procurement, so everything that is really related to the materials that you use in your building. Operational carbon are the emission related to everything that is the life use of the building, so electricity, heating system, so on and so forth. So as you can see here, in the past, with the existing standard, we had very huge portion that was related to the operational carbon, but with the advent of these new codes, we were really able to reduce the operational emissions, but you can see that we increased the embodied ones. This is why, because more we insulate our buildings, so we have more an energy efficient building skins, we're using more greenhouse gas emitting ones. So there's always a balance in understanding these thresholds, and of course, the fact that materials matter. So your design choices matter. And again, if we think about all the objectives, Paris Agreement, whatever you want to think about, and the different scenarios, really related to that 15 degrees Celsius that we saw at the beginning of the presentations, there is really something that really comes to our attention, is that if you really want to achieve a climate neutral, let's say, society, it's not just enough to be low carbon, to reduce our emissions. We have to be more. We have to do more. Really trying to have a new, I would say, a new relationship with every aspect of our life. In this case, let's focus on the design applications. So our way of approaching this problem, we're really focusing on what are called regenerative materials, and really looking at those technologies that were used for thousands of years before the advent of the Industrial Revolution. So there must be something between almost zero emissions, customs, savoir-faire, of all of these techniques that were lost with the Industrial Revolution, and our relationship very detached with the environment, such as we are not a part of an ecosystem, and our aspirations, freedom, and design possibilities of having incredible spans, or this wonderful and marvelous engineering things comes to a cost. So why I believe that these regenerative materials are really the solutions in really trying to heal our relationship with the design, but also relationship with our planet. It's because these materials should support a positive, sustainable development. They should be for people, with the society. They have a low or even a negative impacts and on the environment, but also on the well-being of the users. They contribute to the local economy by fostering local production and job creation. Because at the end of the day, we have to really focus on solutions that can help the whole society in order to be impactful and create a different way of perceiving our future. And they also need to be safe and comfortable solution for the users and aid in the environmental remediation, improving the ecosystems as well. Here, I just wanted to show you some examples, such as straw, mycelium, cork, soil, and bamboo, but there are many more that could be used by following, let's say, these principles. At the same time, one of the problems with these materials is that there are many problems, of course. It's their material variability. So how can we use these materials that seems wonderful for what I've told you so far, but how can we overcome the problems of their variability, maybe less abundance in specific context and location. So this is why, for me, digital fabrication it's a wonderful tool that can really help us reducing the material variability by really working with material optimization, structural optimization, faster speed of construction, and most of all, most importantly, user acceptance. Because as long as we perceive these materials as poor or not contemporary or not worth it for our societal well-being, I think that's going to be a huge, it's a huge problem. So really by working with the, helping those materials land and arrive to a contemporary society, digital fabrication can be a very powerful tool. So today I'm just going to be very quick. I want to show you 3 different scales that really, it's the story of how where I started and where I am today. First, I'm going to show you very quick a methodological approach of database design, because I really want you to understand that you have matrices, indexes that you can use and help guide and navigate this complex environmental situation. The project they have been doing now inside the Natural Materials Lab at Columbia University, in terms of material design and digital fabrication, really understand how to scale up and use these materials with these technologies, and work with the regenerative principles, with communities, and as well as workshop that we did with the students with a large-scale printer. So this methodology, I'm going to be very, very quick. This project is called Material Diets for Climate Neutral Construction. And here, we really wanted to understand, because the question is, we cannot use regenerative materials for everything. We still need windows, we still need foundations, we still need equipments. So how can we understand how to fully neutralize these emissions? And one of the tools, of course, is the use of bio-based materials, as they are absorbing and storing CO2 inside their biomass. And, but it really, there's a huge debate within the researchers on how to quantify this biogenic carbon. So here we use a tool that is the most precise, which is dynamic life cycle assessment, that really calculate the emissions in the moment that they are occurring and in the moment that they are releasing as well. So a very powerful tool to help navigate this debate. And at the end, I want to show you a visualization of the result. So if we think about the current building pyramids, as you can see here, we use a lot of high carbon materials, a lot of solutions that are very, very bad in terms of emissions. So what we propose with this project is to create 3 different diets that we called omnivorous, vegetarian, and vegan, and try to change the building pyramids and maximize the use of carbon negative materials as long as possible. Of course, considering that there are materials that we cannot substitute fully with this one. The concept is very simple. Instead of pulling out non-biogenic CO2 from the soil, we really want to work within the biosphere and the atmosphere. So working at the level of what is already out there. And if there's one concept that I really want you to focus on, is the difference between forests, such as trees, which are called slow-growing biomass as well, and herbaceous and fast-growing biomass. Forests and trees need between 20 to 100 years to fully regrow. So if you want to focus on a solution to store carbon and reach a climate neutrality in 20 years, you immediately understand that that's too much of a risk. Also, if you think about fires, something that is happening a lot in the US, for example, in California right now. So it's it's not wise to put all of your hopes in something that has a very high risk of burning. So this is why if we look at fast-growing biomass that needs from 1 to 4 to 7, maybe years, if we think about bamboo, to fully regrow, we're really working in a very short time scale, and we can really help store and absorb all of these CO2 emissions. And we started to understand how these materials, such as cellulose, hemp, straw, coconut fiber, cork, reed, so on and so forth, how these materials were used in the construction, in the building construction. And of course, the majority of them is used as insulation. So what we thought, can we create a new performance to be coupled with the energy one and really use the ability of fast-growing biomass to store all of these CO2 in the building skins? And as you know, for thermal, let's say, properties, you define a thickness of your building skin in order to achieve specific thermal properties. Here, the concept is the same. Can we define a thickness of your building skin in order to fully neutralize all the emissions coming from your building by using fast-growing bio-based materials? And here, just to show you an example, we calculated all the different quantities according to the 3 different diets. And you can see that the major, let's say, response, the structure is the part that has the highest contribution in terms of emissions usually. So in the omnivorous diet where we had reinforced concrete, you can see that in order to fully neutralize all the emissions coming from all of these elements, we would need up to almost 5 meters. So you see that it's a lot. And at the same time, so if we work with more vegetarian, where we use the solid wood in terms of structure, or a vegan where we use cross-laminated bamboo, you can really see that also according to the different fibers that you use, you can have more comparable thickness as well. So this was just to show you some kind of approaches that you can also have and new performances that can be created considering this climate crisis. Now let's go to the fun part a little bit. And I want to show you the research that we've been doing inside the Columbia University, which is in partnership with Columbia Engineering for everything that is related to the rheology part, and Living Materials Laboratory in Boulder, Colorado, which are the material experts. So this project is really spanning between micro, meso, and macro scale, where we are in charge of the macro scale. The objective of this project was really trying to maximize the fiber content in earth construction, starting with what I just showed you. The possibility of having high content of fibers seems like a very interesting approach to have also when it comes to earth construction. But in this project, we were using 3D printing because it's a technology that it's really pushing the boundaries and the limitation of earth construction, especially when it comes to user acceptance and material optimization. But since this is a new research, we really had to characterize this new material and evaluate also the design possibilities. So where can we use this material for? I don't want to bother you with the context, but if we look at the existing example of 3D printed earth construction, they mostly use a recipe, mixed design, that is similar to cob mixture. And in cob mixture, you have around 2% of fiber content in mass. What we were able to achieve with our research is starting with a mixed design that is similar to the cob, so from 2% of fiber content, up to what we were able to achieve of 13% of fiber content. So you have to think about that the limitations of adding fibers in 3D printing is really related to the viscosity of the materials. You have to have a paste that it's extrudable, but you also need to work with the pumping system. So it's not just about adding fibers. You really try to understand all the constraints inside this technology. And the fact that the reason why we wanted to maximize the fiber content, of course, it's to not only to increase the ability of storing carbon in these elements, but also to reduce the shrinkage, which is a characteristic that is very common in earth construction. Reduce the density, so having something that is lightweight, because earth construction is perceived as very massive, and reduce the thermal conductivity, so improve the thermal properties of these techniques, and increase the ductility and mechanical performances, because you're going to have fibers that are really helping different behaviors. In order to do that, besides soil and, for instance, different fibers, we really had to work with materials that need to help us working with the viscosity and the rheology of the mixtures. So this is why we started to work with different biopolymers, food-grade polysaccharides, which are very used in traditional earth construction. So if you go to different regions of Africa, they'll be using a lot of karité butter, really to help preserve the plaster outside the earth construction. They're using blood to really help the stability of this material. So there's a huge knowledge of using of these bio-based materials in the earth construction that has been lost in the past. So we really wanted to use them and help us achieve a specific fluidity and properties to make this material extrudable for our applications. And what we understood is that it's not just about the different biopolymers that we can use. There's also a magic that it's happening at the macrostructure between the clay particles, plates, different kind of charges, the biopolymers as well that are creating some sort of paste, ductile happening between these minerals, and at the same time, what is happening also by using different kind of fibers. So we developed specific mixed designs according to different fiber used, according to different biopolymers that we were using, and really having a spectrum of possibilities. So according to the location where you are, you have a specific clay minerals in your soil, you have a specific fibers that you have abundant. So really translating this research finding according to your location was one of the most important achievements that we did in our research. And then we tested the materials in order really to understand their properties. And if you can see here, this is the soil control, so no biopolymer and no fibers. You can see that the rupture, it's very brittle, so it stops immediately. But with the addition of fibers, you can really see that the plasticity, it's happening a lot. So there's really something that is happening with the inclusion of these elements. But then we said it's not just about the materials. We're using a technology that can really help us play with different geometries. So we tested different cross-sections, really to understand if we could improve also the mechanical properties of these elements. And what we realized is that, of course, the geometry plays an incredible role. So this is, of course, according to the load direction. So if you have a vertical load, you need the best cross-section is where you have more rigid wave on that direction. Whereas if you add more cross-passed, of course, that is not really helping the direction of the load. But again, then we could work with more torsion. So it's really a question of combining the application of what you want to achieve, the geometry, and the materials. And then we were really questioning the idea of the heaviness of earth construction. So why can we try to design elements, partitioners that could be very lightweight? And what happened is that we really tried to work with the Mashrabiyya pattern from the Arabic and Islamic culture, really to create these modules. And then by placing them on specific shapes and by using the fact that just by drying together these materials that they were just opposed, by drying together they were creating some sort of glue, we were able to achieve ideally infinite surfaces by just having this single module that were just connected one to the other. And the final results was exhibited in a space in New York, which is called 114 Space of Ideas. And it was really interesting way of seeing how lightweight Earth can be as well. And there's another line of research that we are developing also in terms of contour crafting. So really understanding how to design the printing path in a way really to mimic basketry, vessels, and really see how these materials also can be formed and create interesting shapes. I don't know how familiar you are with the clay or soil printing, but this looping, they're very impossible to achieve with clay printing. So really the fact that we have these fibers inside are really helping us in the freedom of creating these artifacts in a way as well. And nonetheless, what happened is that there are very little information regarding the carbon footprint, so the embodied impacts of these biopolymers. So I only found few references, and unfortunately, the more we add these biopolymers, the less environmental friendly we are. So again, there was a huge debate within our research group. And this is why I really start questioning the use of these biopolymers in a, let's say, market way. So of course, if I go to a chemical industry and I purchase these biopolymers, the environmental impacts can be very high. But what happens if we use these biopolymers that are readily available, coming from other industry, and therefore closing some sort of, in a circular economy way, and helping really to restore the climate according to the regenerative principle that we were talking about before. So this happened when I did a collaboration with a Mexican architectural firm, COA, and we decided to co-design with the Oaxaca community in Mexico. And in this region, it's very known for the production of mezcal and tequila. And I don't know if you're familiar, but for every liter of mezcal and tequila, there are 10 liters of wastewater that are produced typically that are just discarded without concern. And they're creating huge environmental impacts on the location where these liquids are discarded. So the idea was really and this water is full of biopolymers coming from the production of mezcal. So what we decided to do is to really reuse what they are using in COA in Mexico is really using this waste stream for earth construction and help having the same potentials and results that we saw with the chemically purchased biopolymers, but by just using a waste one. And at the same time, really to working with the local communities and understanding that this can really help, not just the environment, but in a way, but help also them understanding of how we use valuable resources in the area was a very interesting point for me. So they were using their expert in traditional earth construction, the use of this biopolymer and fibers from the mezcal industry. We really wanted to use digital fabrication to help creating, to minimize the use of materials. So we were able to achieve the same performances, but use 50% of the weight. So what we did, we designed a mold, really trying to minimize the use of the material, and then creating different kind of strategies to demold it, help it, so on and so forth. The same thing that we have been doing in the workshop, in a way. And what was beautiful to see, it's really the women of this community that the mezcal industry is very male-oriented. The mezcaleros are really considered in charge. But what is happening is actually that the women as really the force that sometimes are left behind of the curtains. So it was really beautiful to see their handcrafts, the manuality, and the joy of working with these materials and all the ideas that were coming out of the possibility of using something that is lightweight for them, so it was easier to maneuver. So again, where design and materials can really be helpful in a way. And at the end, these tools that were bricks, construction elements, so on and so forth, were exhibited at the Mexico Design Week 2024. And we won the material recognition for this project. I'm going to be very quick because I want to be mindful of time. It's okay. And I just want to show you an example of a large-scale fabrication workshop we did with a Columbia student. It was a 5 days hackathon, and what was really impressive is that the students, the majority of these students had zero or almost zero experience in terms of digital fabrication, and also how to design a model. They had zero experiences with Earth. So it was so powerful to see that this material is so accessible, and this technology can be very straightforward with a few basics, and really to see what was able also to achieve in 5 days. But nonetheless, one of the most important takeaways of this workshop for me was to learn to teach the students how to cope with the digital fabrication frustration. Because what you perceive, it's a wonderful technology that you just press a button and everything works smoothly, but I guarantee you that this is not the case. There are so many issues. The material is not working. One day it rains, you don't know why, the machine doesn't want to cooperate. The file is not working. So there are so many issues that can happen. And for me, that was one of the most important things, really, to teach the student how to not take these things personally, but as an opportunity to learn something. So we really had to work with these big machines, which is called SCADA from 3D Potter, and this pumping system that for us was the enemy, because each pumping system have a limitation in terms of aggregates that you can use to 3D print. So instead of our 13% that we developed for the printing system in terms of fiber content, with this pumping system, we were only able to have 4% of fiber content in terms of mass. Still. So, but you really see that the limitations it's in the technical solutions. And then the students, you're gonna see now when you work with Earth, you need to print a certain amount of layers, and then you need to wait for the day after to be fully dried, so you can print again on top of it. So by only having 5 days, we could only achieve a limited, let's say, height of elements, but nonetheless, it was very interesting. And what I want to really show you here in this video is how forgiving Earth is. This is something that you cannot do with cement and concrete. Look, here we are printing, something went wrong, but just manipulating with our hands very quickly, we can just start printing again. Or if we don't like what we did, we just can collect all the materials, put it back again into the pumping system, and start again. You have a long time in terms of printing span. With cement and concrete, you have 10 minutes. Then that's it. The material is curing. So it's very, very forgiving when it comes to really learning a technology as well. And here, just to show you the final elements that the students were able to create, they created some sort of column that we used half of a column that we used to create a coffee table, and this bench where you can really see all the fiber reinforcement details that were really helping different line paths to stay together. And nonetheless, we really wanted to question with the students, okay, we did all of this, but can we reuse this material once it's dried? So it's always, for us, workshops are always a question and a moment to learn new things. And so we developed the recycling strategy and protocol. So after we completed the material, we soaked it again, and then we tried to print it again and create this circle. And first, we tested the compressive strength of both the new and the recycled mix after 9 days and 28 days. And what was very interesting for us to see is that the strength remains more or less the same. So this suggested that our materials can be reused, is not losing any of the properties. But nonetheless, when we tried to print it again, we realized the materials had a lot of clumps inside. So in order to print it again, we need to add more biopolymers. But adding more biopolymers can increase the issues in terms of environmental impacts if you're using biopolymers that we are just buying as they are. So this really started helping us mapping the situation of the materials we are developing and the technology. So we always want to be aware of the limitations and be honest on what is happening with what we are developing. And this is just to show you an example of the final elements that were exhibited inside Avery Library at Columbia University. And all the students very happy, despite the ups and downs of the 5 days. So at the end of every day, we had like 10 minutes of, okay, what went wrong today? A huge list, and take it as a starting point for the next day. And so this is it. I hope you enjoyed it, and let me know if you have questions. Même en français, si vous voulez.
Thank you, Olga, for this presentation. Est-ce qu'il y a des questions? Oui, en français ou en anglais, c'est comme vous voulez.
I leave the happy faces.
Vous nous avez montré des objets comme par exemple une chaise ou des parties d'une table, enfin qu'on peut assembler une table, mais je me suis posé la question de est-ce que on pourrait par exemple faire des cloisons préfabriquées en terre par la suite dans un futur, enfin est-ce que vous pensez que c'est possible?
Merci pour la question. Wait this summer. You will see this summer. Stay tuned. Non, tu vois, parce que c'est juste une question d'opportunité. Nous, on n'a pas un grand labo, donc il faut organiser des workshops ou des événements pour utiliser la large-scale printer. Et là, maintenant, on va faire des expériences.
D'autres questions?
Well, okay. I just wanted to ask if there's a limit height to what you're gonna build with this printer. I mean, in order like to make a wall, as it was said before, how do you proceed? Can you print a whole wall, or do you proceed by adding bricks, maybe, that are prefabricated with this printer?
Thank you for the question. I think it really depends what you want to do. So if you want to have, usually in digital fabrication, in additive manufacturing, there are two ways of building. One is off-site and one is on-site. So if you go with the off-site solutions, you can print all your components, in your fabric, which is very controlled in terms of temperature, humidity, and you can really have everything under control, but you're limited in terms of the size of the elements that you want to print. Or you can work on-site and therefore use these big printers and print the whole wall systems, and then finishing with the different kind of plasters or element that you want to add. It's really, I think that additive manufacturing is still trying to understand how to find this specific path as a technology for large house, let's say, systems. Because if we think that we're going to use digital fabrication to print squared house with the same, let's say, structures or geometries, I think we're losing some kind of opportunities in a way. And so if you go with the example, let's say the on-site technique, usually I think research, the past example, they were able to print around 60 centimeters. Then you have to wait for the night, and you start printing it again. Because the materials, by drying, it's really gain strength. So you really need that strength to be able to support the load of the next layers. And otherwise it would collapse because there's the weight of the water and the weight that it's really pushing down. So there's so many opportunities still untapped and unexplored. And the construction industry for 3D printing is not yet an industry. So they're really trying to define themselves in a way. Okay.
I was very fascinated by the last part of your presentation, and I was also asking myself, so we are saying we use materials that you can find on site, plus some added things that should be researched in order to be also sustainable and so on. But I'm thinking about a practical use of this technology. Like, so you need the materials, but you need also the technology for the printer, no? And is it possible, or is it already in search? Is there a direction of the search how to make accessible the construction of a printer? So let's say I want to make 5 houses in Brazil or in the south of Italy or somewhere in the world, and I have access to the material and also to the chemical. But this printer, is it possible to make a open source technology that everybody can build with easy material, like with steel and, I don't know, the printer, and then add the technological part so you can bring there on site all the computers and, I don't know, technological wires and so on, and then you build the big printer, and you on site, you make then this. Is it like, I don't know.
Thank you for the question. I think you touched a very important points, which is labor skills. Because when it comes to digital fabrication, you need workers that are trained in terms of material, technology, softwares. So there's a lot of skills and knowledge that need to be gained. And I really believe that universities or different kind of educational bodies can really play a huge role in disseminate the languages that is needed in terms of the basics. Another thing is that if you start digging into the earth construction world, and especially the additive manufacturing construction world, you're going to see that people are so generous. And the idea behind 3D printing was really to create open source softwares, open source G-codes, which is the file that it's translating your geometry in a printing path. So this is the aspiration. And really people want to work with community. They really want to use local materials, everything that is available on site, and you just ship the technology as it is. So this is the aspiration. And I really believe that maybe the constraints are still acceptance, in a way, insurance, and codes. So, but we have to start, no, somewhere and show that it's working, it has a potential, and I think design and architecture is very powerful because it can really inspire by showing to the people that it's possible. And I think there's so much more that we can do that we still don't know, because we're still doing squared house with this technology, which doesn't make any sense. I visited a neighborhood, the Icon, printed in Austin, Texas. It's like 100 houses completely 3D printed. And you can really see that the shape, because you also need to, would you live in a house with all the layers showing? You see what I mean? Because you really see all the layers. So of course, maybe you start by doing a squared house, then you have to solve the issues of the layers. So it's a dialogue with the users. It's a dialogue with the inhabitants. It's a dialogue with everyone. But for sure, I think there's a lot to do still. But it's a lot of fun. I don't know if I answered your question.
Yeah.
No way, no way.
Yeah. More to think about.
Yeah.
D'autres questions? Oui.
It's kind of a question that is a rebound on what Mr. said. We see in 3D printing, I mean plastic 3D printing in small scale, that it's something that is gaining traction in the public, so much so that the manufacturers of 3D printers, such as, I don't know, Bamboo Lab, for example, are using apps and making it very user-friendly. And I think, I don't know which direction you think this should go for, like, housing printing or building printing, where is it someone who has skills that are passed down and the skills are become so mainstream that everyone can use it? Or is it someone has the skills and makes the software or something that makes it user-friendly for everyone?
Thank you for the question. For sure, softwares, it's a problem, it's an issue. For instance, I create all my scripts in Grasshopper, because I really want to be in control of the whole process. But that's a skill to gain. But nonetheless, there have been so many, I don't know, for instance, in robotic fabrication, it's very hard to visualize the path of the robotic arm with 6 axes, and there's a lot of very expensive softwares that help you to do it, and I'm sure that little by little people are gonna develop accessible tools, and it's something that it's coming for sure. It's something it's coming, but I really believe that it's also important to understand the technology. So even if you have a very easy tools for the geometry and the G-code creation and the machine movements, so on and so forth, I think it's very important to understand how it works as well. So you can really dive into the problems. For instance, for the workshop, we had the problem that since we were printing different things all together, what the printer does usually, it starts like that, and it goes immediately down. But you understand if she goes, I say she because in Italian it's a female, if it goes down immediately, you're gonna hit elements that are on your path. But if you know how to create the code, then you know how to make the machine does this and then down. You see what I mean? This is maybe a silly example, but there are things that you need to know in terms to have the total freedom of using this technology.
Maybe my question wasn't, English is not my main language. My question is, do you think that it's a path that is someone has the skills to make a tool to make it easy for others, or
Sure.
the skills get passed down so much that everyone knows how to use it?
You mean, I'm not sure I understand the question.
Well, for example, with computer science
Yes.
and computer usage in general,
Yeah.
a few decades ago, it was something that was extremely niche for very skilled people with very sharp knowledge on the thing. Today, it's become computer usage is a daily thing on our wrist, on our phone, even on our glasses now. My question is that if you think that the path that this technology will go through is usage that gets so mainstream that everyone knows how to use it, or it will need a translator that will be able to make a tool to use it without having the very pointed and sharp skills?
Both. And I mean, we still need IT to help us understand how computer works. So of course, I'm sure that it's going to be very accessible, but you're still going to need people who help us maybe navigate the details. But I'm sure it's going to be very available. Thank you.
D'autres questions? Non? Oui.
First of all, thank you for the presentation. And also, I have this question about, I see Earth construction as like a very low income, like everyone can do it. It's like you can use the resource of where it comes from to make the house, and like even the children can build it. Like it's like very easy material to use and doesn't need like it needs skills, but like it's very accessible and you can learn very easily. And so I'm quite wondering about like this way of using Earth. Is it going to be like more of a high-end way of using Earth, or is it like, do you think it like helps, or is it going to be like in contrary, like in competition with like the more traditional way to use Earth as we used to do it?
I don't, thank you for the question. I don't think one way it's in contrast with the other. they can both work together. But working with earth, it's physically very intense. You can ask Arthur over there, and it's so hard, so physically needed. So see the use of this technology as a helper. People are just really developing extruding system, not just for 3D printing, but also to ram earth with the use of machines. So machines, it's really there actually to help make it more, not mainstream, but more accessible really in terms of the labor that it's needed.
Another question. Did you also do some trials with heating or baking? I don't know if with earth you're able to do it, maybe with other materials, but that you create an element that should be perfect, but you see the imperfection, that it gives a bit of an artisanal touch to the element that you're doing. So that you bake that thing, is it possible to maintain that thing for a longer period?
I'm not sure. Can you please be quiet? I couldn't hear very well.
So my question is, you're working mostly with earth, and I don't know if it's possible to do it, to bake the element that you 3D printed.
Ceramic. So you want to do ceramic?
In a way, a ceramic, with that argile, I don't know. But you 3D print it, and with this imperfection, that you create elements that could be used also in architecture as decorative elements, maintaining this artisanal look, a bit more rough, with this roughness of it.
Sure. You can. There are people who actually you can burn them. There are kiln, and you can fire the elements. Just consider that we have a lot of fibers inside. So if we burn it, the fiber is going to burn, and you're just going to have more porosity. Okay. So that could also be a strategy.
Okay.
Thank you.
Thank you.
Okay. Thank you very much. So if you want to ask other questions to Olga, you can find her in the Salle XP or in 125 room. See you later for the next conference, and thank you.